Reading quiz number 33 is possibly one of the more important reading quizzes and more useful reading quizzes that we'll start to use in the second semester. And it's all about the fundamental theorem of calculus part 2, or what we will call part 2. And it's all about what we can do to evaluate definite integrals. It's going to make that connection between definite integrals and antiderivatives that'll be so fundamental for what we do with our applications of integrals later on. So as stated before, the fundamental theorem has two parts. The part we are about ready to study is by far the most applied for this class. It allows us to determine the value of a definite integral by just knowing information about the integrand's antiderivative. And what it states is if f is continuous on the closed interval a to b, then the integral from a to b of f of x dx equals capital F of b minus capital F of a, where capital F is any antiderivative of f. And by antiderivative, again, we mean a function such that capital F prime is equal to f. This is something we can quickly prove if we have part 1 of the FTC that we discussed in a previous reading quiz. And basically, if you remember, that states if f is continuous on a closed interval a to b, and we define capital F of x to be equal to the integral from a to x of f of t dt, that's a continuous function on a closed interval a to b, differentiable on the open interval a to b, and is an antiderivative on a to b, which meant that capital F of x prime is equal to f of x. So with this first part in hand, and knowing that capital F of x is defined as the integral from a to x of f of t dt, then all we need to do is plug in b and a, and we get the integral from a to b of f of t dt minus the integral from a to a of f of t dt. And if you remember from one of our definite integral rules, the integral from a to a of f of t dt is just 0. So we're left with the statement that capital F of b minus capital F of a equals the integral from a to b of f of t dt. So let's talk about how to evaluate definite integrals using this technique. You'll want to find the simplest antiderivative. Now, if you remember from a previous reading quiz, we talked about antiderivatives and how they have the plus c, indicating that there are an infinite number of antiderivatives that would fit the bill, depending on which constant you choose or are required to have. But in this case, we want to find the simplest antiderivatives when we're going ahead and finding our definite integrals. So what this theorem says, the fundamental theorem of calculus, all we need to do is find the antiderivative, plug in the upper and lower limits, subtract, and evaluate. So our example here, the integral from 1 to 4 of x squared dx. So again, notice that when we find an antiderivative, we don't need to use the plus c, because eventually the plus c's will cancel out in the long runs. So we've got x cubed over 3 as an antiderivative. And then when we rewrite, we're going to say the integral from 1 to 4 of x squared dx equals x cubed over 3 from 1 to 4. Notice the little bracket here, which indicates that we're still going from 1 to 4, and we're going to plug those values into our antiderivative. Plug in the upper limit first. We get 4 cubed over 3. Subtract what we get when we plug in the lower limit, which is 1 cubed over 3, and evaluate using arithmetic. We get the value of 21. And what does that statement mean? So a little reflection would state that this is saying the signed area between y equals x squared and the x-axis is 21 units squared. So let's try another one. The integral from 1 to 3 of dx over x squared. So we need to find the simplest antiderivative. If we rewrite this function as x to the negative 2, the antiderivative is x to the negative 1 divided by negative 1, which can be rewritten as negative 1 over x, a common antiderivative that we should know. And then we evaluate the antiderivative at the upper limit and subtract the antiderivative at the lower limit. So again, the antiderivative, the simplest one was negative 1 over x. We're going to go from 1 to 3, so we got the little brace there. When we plug in 3, we get negative 1/3 minus a negative 1 over 1. So it turned out to be a plus there. 1 minus 1/3 is 2/3. What are we saying? This is saying that the signed area between y equals 1 over x squared and the x-axis is 2/3 units squared. Keep on going. More examples. The more examples you have, the better you get at this. And there's not too much I can say other than you need to look over your antiderivatives. They are going to come up all over the place. They're going to be all kinds of different types, and we just need to be able to spot them. Usually the calculus part is okay as far as applying the FTC. Sometimes the arithmetic can be challenging. So here's example 3. Integral from 0 to 2 of e to the x dx. Antiderivative of e to the x is e to the x. We're going to go from 0 to 2. Plug in 2, we get e squared. Plug in 0, we get 1. So our final answer is e squared minus 1. Integral from 1 to e squared of dx over x. Remember, the antiderivative of 1 over x is natural log of absolute value of x. Make sure you include the absolute value there. We're going to plug in e squared, which is a positive number. No need for the absolute value at that point. And then we get plug in 1, and we get natural log of 1, which is just 0. Remember, natural log and e are inverse functions, so natural log of e squared would just reduce down to 2. More examples. Integral from pi over 4 to 3 pi over 4 of cosecant of theta times cotangent of theta d theta. This is where knowing your list of trig derivatives and antiderivatives is very helpful. The antiderivative of cosecant of theta, cotangent of theta d theta is negative cosecant squared of theta. We're going to plug in 3 pi over 4, and we plug in pi over 4. So negative cosecant squared of 3 pi over 4. So let's think about this. So at 3 pi over 4, sine is equal to root 2 over 2. So that would mean that negative cosecant would be negative root 2. We're going to square that. So we get negative 2. And then we're going to get the same at pi over 4. So those cancel out to be equal to 0. Integral from 0 to 1 of 1 plus 1/2 u to the 4th minus 2/5 u to the 9th du. Looks a little more complicated, but here you want to make sure that you're careful with what you do. So the antiderivative itself isn't too challenging. It's going to be u plus u to the 5th over 10 minus u to the 10th over 25 from 0 to 1. And we want to make sure that when we write this out that we're going to plug in everything. We're going to plug 1 into everything first and subtract what we get when we plug 0 into everything. And when you work that out, you get 53 over 50. So example 7, integral from 1 to 4 of f prime of x dx, assuming f prime is continuous on the closed interval 1 to 4. Well, I don't give you very much information, but we do know the antiderivative, the simplest antiderivative of f prime of x would be f of x. So our answer would just be f of 4 minus f of 1.